Hello, everyone, and welcome to our presentation. I'm Will Lovett. I work for the compiler and library development team at ARM, and I'm very pleased to have with me Konstantinos Margaritis, the CTO of Vectorscan, who is going to be talking about Vectorscan's experience in porting Hyperscan to the ARM platform. After this, I'd like to share some results of enhancing this port to use the SVE2 vector extension. And finally, I'd like to give some general guidance when porting your code to use SVE2. So we have a lot to cover, so let's get started. Konstantinos, over to you.
First, I'd like to do a small introduction. Who is Vectorscan? We are a small startup established in 2020. However, we have lots of experience in SIMD optimizations in almost all major architectures. I have been personally active in free open source software, being a Debian developer since 1999, involved in porting to other architectures, namely PowerPC and ARMHF. Vectorization and software optimization is almost a passion of mine, and the next logical step was to create a company around that. Now to our topic. What is Hyperscan? Hyperscan is a high-performance multiple regular expression library in C++, starting in 2008 by Sensory Networks Incorporated, acquired by Intel in 2015, and released as open source software under the BSD license. Originally, it was portable, but Intel optimized it to its own architectures using SC AVX2 and later AVX512 optimizations. It is currently used in Snort and other deep packet inspection software and real-time packet analysis. Its advantages are its high performance and parallel matching, however, at the cost of lack of portability and difficulty to debug. So I think it's in order to give you a short history here. In the summer of 2020, ARM approached Vectorscan to complete an ongoing port of Hyperscan to ARM 64-bit architecture and upstream the changes to Intel. We were not the first to do that. There were a couple of existing ports already, namely Marvell, who tried to do this before. There were many challenges in this effort. First, all SIMD code was mixed with logic code. Some SIMD abstraction was introduced, but it was x86 only. And every algorithm had a separate implementation for each sub-architecture, SC, AVX2, AVX512, including most or all helper functions involved. Now, in order to ensure upstreamability, the porting approach was split in three phases. Splitting the architecture-specific code from the logic code, port only the architecture-specific code, and ensure all unit functional tests pass. And the phase 3, of course, was the optimization phase. Phase 1 involved most of the refactoring in order to eliminate most x86 specifics from the algorithm code. Namely, some very important step of that was to replace all x86 intrinsics and x86 assembly with wrappers. The phase 2 was the actual ARM porting of the respective header files. It involved adding generic implementations for 256, 384, and 512-bit vectors, as there was usage of those in the code. In ARM's case, it would just fall back to 2, 3, or 4 128-bit vectors. We also added some extra functions to make up for missing BMI functions on ARM, namely pdep and pexp. Phase 3 involved lots of testing and micro benchmarking, adding cache prefetching and using profiling tools to find and tackle CPU hotspots. Many algorithms were refactored to reduce random memory access. A particular example is FDR.C. Initial results showed some promise in comparison to the original Hyperscan. Our biggest fear was that in going for portability, we would lose performance. We did lose performance, but not as much as we feared. To continue on the story, at this point, we submitted a couple of pull requests to the original Hyperscan project. After a long delay, we got an official reply that Intel will only support x86 and will not accept patches for other architectures. And thus, Vectorscan was born. Its goals to be portable, 100% API and ABI compatible Hyperscan drop-in replacement. support every major architecture and all SMD engines. As performance is regarded, we should perform equally to or better, if possible, to the original Hyperscan project, but not at the cost of portability. If someone really needs maximum performance on Intel architectures, please use original Hyperscan. Furthermore, one of the benefits of using a separate project was that we had the luxury to simplify and modernize the source code as we need, something that we could not do in the original project, at least not as easily. Following that decision, we started a longer term project to refactor the Vectorscan. So it was split in two steps. First step was to clean up the code. That involved removing long C macros, hard to debug and profile, and replace them with static inline functions. Upgrade compiling standards to C17 and C++17. Remove Windows support. If you really need that, please again use the original Hyperscan project. Now for the second step, we introduced a new C++ template vector class, super vector class. That enabled us to replace 3 times the algorithm implementations that we had and all the accompanying helper functions with C++ template functions. We managed to keep the same performance, but at the 1/3 of the code size, as the optimizations were compile time and inlined. That also enabled us to provide a portable SMD engine implementation, almost size agnostic, with sane fallbacks. This means that we could use a larger vector size, which would fall back in the end in what our platform supports. So the status so far, we have completed the Noodle, Truffle, and Shufti matching engines ported to the new class. As expected, we have 1/3 of the code size, no visible loss of performance, and the work in progress for the rest of the engines. In parallel, we developed and added a new micro benchmarking tool specifically for these engines to fine-tune performance of those. A few words we should say about the super vector class. The plan is to offer a portable way to write vector code in the form of a C++ compile time library. We will try to imitate the ARM Neon advanced SIMD design, which is still a work in progress, as this is orthogonal and very clean design. We will try to use C++ features such as const expressions and template arguments as much as possible to ensure compile time inlining and avoid runtime branches. As mentioned, we will try to provide a vector size agnostic method to write the same code. For example, if you have an algorithm that requires 256-bit vectors, but your platform only provides 128-bit, you can use that 256 vector and the library should fall back to two times the 128-bit vectors. Many similar libraries exist, but most wrap around existing vector engines. We want to provide a higher abstraction of the SIMD engine and then fall back to the actual hardware. As a longer term, we plan to separate this from a Vectorscan into its own project. The reasoning for developing this around Hyperscan is that it gives us the benefit of finding and solving actual problems, real-time problems with and bottlenecks around a real project. Now back to the Vectorscan results. These are the current numbers we are getting. The numbers are slightly different from this previous slide. The reasoning is that they are now running, all numbers are inside a virtual machine instead of bare metal. So Intel numbers are a bit lower than before. However, on the ARM side, they are higher. As you can see, the ampere, even inside a VM, more than matches the respective Intel. And we ran them all on the same spec virtual machine. Before I pass on to Will, I would like to mention the roadmap. Obviously, we have lots of optimizations and refactorings to do on the code. But since the groundwork is done, we also plan to port more architectures and improve the existing ports, including SVE2. Since it is a drop-in Hyperscan replacement, a logical step is to provide a package for most important popular Linux distributions. We will start by Debian and by extension Ubuntu. Red Hat will follow, and thankfully Alpine Linux already includes Vectorscan by default. You can find the code in our GitHub repo, which is listed here. That is all. We hope you found it interesting. Regarding SVE2 in particular, we have been working with a team in ARM towards that goal. And now I'd like to hand over to Will Lovett from ARM, who will present the results of that effort.
Thanks very much, Konstantinos. One of our development team here at ARM has been building upon Konstantinos's work and adding SVE and SVE2 implementations of some of the key regular expression matching engines in Vectorscan, which are listed here. All this work has been integrated into the public development branch of Vectorscan on GitHub and is also available as a stable branch named develop-SVE2. We used these implementations to execute the Hyperscan benchmark suite, and in particular, two benchmarks that are representative of workloads in Snort, the open source deep packet inspection software mentioned by Konstantinos earlier. The results shown here are pre-silicon estimates of the performance that we expect from the upcoming Neoverse N2 processor, which implements SVE2. It's worth noting that Neoverse N2 has the same total vector capability in both the Neon unit and the 128-bit SVE2 vector units. So comparing the two is a fair comparison in terms of their capability. Now, 0% on this graph represents the performance of this system when run using Neon instructions. So as you can see, we see a nice benefit from making use of the SVE vector units and a nice additional benefit of SVE2. This is interesting. It comes down to utilizing two new instructions in SVE2 named match and nmatch, which were specifically added to allow vectorizing the scanning of character strings. This code was implemented using the SVE2 ARM-C language extension, or ACLE, and is written in such a way as to fully utilize the SVE2 vector units, regardless of how wide those SVE2 units are. We call this vector length agnostic programming. This allows the compiled code to be future-proof. It should run correctly on future SVE2 systems and take full advantage of whatever width of SVE2 registers the hardware has available. So for the final part of this talk, I'd like to provide some advice when porting your code to SVE2 to ensure that your code is portable across different implementations, as we've seen here for Vectorscan. So this table compares the options you have for generating SVE2 code. Firstly, you can use the ARM-C language extension for SVE, as we did with Vectorscan. This is recommended for optimized libraries and frameworks like Vectorscan, where you want direct control over the vector instructions used. When written carefully, the resultant code is vector length agnostic and fully portable across different implementations of SVE2. We would still recommend testing your code with multiple vector widths to guard against bugs that break vector width portability. For users without vector intrinsics in their code, the simplest way of making use of SVE2 is to rely on your compiler to optimize your scalar code using auto-vectorization. GCC has mature SVE2 auto-vectorization today, as has ARM compiler for Linux, our commercial compiler. We're working hard at enabling SVE2 auto-vectorization in the LLVM ecosystem, and it should be available in LLVM 14 and improved further in LLVM 15 next year. And we're also going to be enabling it in ARM compiler for embedded. All of these compilers will generate vector length agnostic SVE2 code by default. Now, I'd like to introduce a new flag shown here, which is called -m SVE vector bit, which is then you give an argument, which is supported in open source GCC and in open source LLVM compilers, and will be available in a future release of ARM compiler for Linux and ARM compiler for embedded. This flag is a message to the compiler that allows the compiler to assume that the code will only ever be executed on an implementation with exactly the specified SVE2 vector width at runtime. Now, there are a small number of situations where this is a useful and legitimate assumption to make and to make use of, but it is important to recognize that you pass on this assumption and its consequences to anyone who uses your binary. If executed on any other runtime vector width, the code may break in unexpected ways, and so consequently, we recommend you avoid using this flag for ACLE code, especially for any code that's distributed in binary form. A more portable alternative to using this new flag is to write your code using the SVE2 ACLE, but carefully ensure that all of the operations disable everything past the first 128 bits of your SVE2 registers using predication. Now, this has some nice properties. It allows interoperability of Neon and SVE2 instructions, and it also allows code to be executed correctly at all runtime vector widths. It's a good choice for making use of SVE2 features in legacy frameworks that rely on a known vector width, maybe as part of the API that you present to the users of libraries, or to those which need to store vector variables in structs and classes. I don't have time to go through the detail of that, but I'd refer you to the ACLE specification, which talks about that in more detail. One of our partners is currently undertaking an effort to port the C++ stud experimental SIMD library to make use of SVE2, and they're making good progress with the approach shown here. If you are interested in porting such a framework to SVE2, then we would invite you to get in touch with ARM and we can help support your efforts. Finally, it's possible to make use of the -m SVE2 vector bits flag in C and C++ source code with auto-vectorization. Again, this allows the compiler to assume that this code will only ever be executed on exactly the given vector width. Therefore, this resultant code will have undefined behavior when executed on machines with other vector widths, so it's not recommended for most users. And then for completeness, you can write assembly files or inline assembly directly. This gives you complete control over exactly which instructions are used and the registers that are allocated for those instructions, but it also means that you're responsible for ensuring the portability of your code, and that code will generally be harder to maintain than similar code written using the ACLE. This is suitable for very low-level code, such as in the core of operating systems and in firmware and so on, but it's not recommended for application development. Before we finish, I'd like to highlight some places where you can get more information about SVE2. If you search for the words SVE2 Programmer's Guide, you should find our main site on developer.arm.com, which has a heap of technical content for developers to make use of SVE and SVE2. Briefly, these include technical introductions and reference guides to the architecture itself, a newly updated guide for migrating code from Neon to SVE, a brand new optimization guide around use of SVE2, SVE and SVE2, a updated guide for porting and optimizing high-performance computing applications with SVE, a new tool we're very excited about, which is an interactive search engine for finding ACLE functions to do whatever job it is you're trying to do. This should make it much easier to work out what the name of various ACLE functions are and how they work. And finally, a new section which highlights developer blog posts relating to SVE and SVE2. Speaking of which, we're intending to add a bunch more SVE2 content over the next year, which includes a blog series that will be well worth reading called Thinking in Parallel, which will explore some practical real-world examples of making use of vector instructions on ARM, and a new blog and white paper on making best use of SVE2 for machine learning workloads. So that's all that we had for today. So I'd like to close by saying thank you to Konstantinos and to the Vector Camp team for their great work on Vectorscan. Thank you. And thank you very much for joining us in this presentation. We hope you enjoyed it, and we hope you enjoy the rest of Dev Summit 2021.